Hello everyone, I am your good friend. You can call me Curioscope. Starting today, I will guide you to explore the unknown, the curious, from space to the universe, from particles, atoms to protons. Today's video will start from neutrinos and dark matter in 10 aspects, such as black holes, atoms, and molecules. Take you through the understanding of how the universe actually began. 13.8 billion years ago, the universe was born. The second before was a void. The next second is filled with infinite possibilities. This may be the greatest puzzle in all science. It spans theory and experiment, the boundaries of physics and philosophy. Our understanding of the universe depends on mechanism and causality. We strive to understand why things are the way they are, but at the most fundamental level, we still do not know how or why the entire universe formed. The lack of this explanation is not due to a lack of exploration, as the famous cosmologist Stephen S. Hawking once hypothesized, before considering space and time as inherent properties of the universe we inhabit. Perhaps there was truly nothing. The beginning of the universe marks the beginning of time, and space cannot exist before time. Therefore, the universe cannot exist either, considering the geometric shape of space-time. Going back to different eras, Hawking saw it contract and curve, finally tending towards roundness, looking for something that transcends time and space, just like searching for something north of the North Pole. It's meaningless, or perhaps there was no real beginning at all, but rather the limitation of our observational ability. Scientists believe it is the period of exponential expansion known as the Big Bang that brought the universe to its peak. The Big Bang laid the foundation for everything that followed. Our universe, after an extremely short second, stopped inflating. But some physicists believe this is not the only period of expansion in the entire universe. On the contrary, inflation will continue forever elsewhere, producing distributed in the powerful eternal multiverse. The foam universe in it, or our current universe, is merely a series of long and possibly infinite expansion and contraction, the latest one in the universe. This theory is called the Big Bounce. Instead of coming from nothing, then it expands exponentially to reduce the structure we see today. Contemporary physicists, as Paul Steinhardt thinks, everything in the universe, as periodic growth and contraction, or our understanding of scale, is fundamentally incomplete. Physicist Roger Penrose considered the properties of shape, and without considering their size, and believing we can do the same to the universe. In this view, the universe at infinitely small and infinitely large, lost sense of time and scale, become identical in all intentions and purposes, whether on a chessboard suitable for your pocket, or spanning the entire courtyard. Perhaps our universe originated from a brief dimension collision. String theory attempts to explain the fundamental principles of reality, believing that there are 11 dimensions in hyperspace. The tiny vibrating strings in reality make up the 3 spatial dimensions we experience. In one time dimension, the 3 spatial dimensions we experience in the universe. In a time dimension, simply one part of the whole, the beginning and growth of the brain universe, originating from collisions of higher-order brains. Perhaps there are other things, somewhere in mathematics or physics, that we have not yet touched upon, and that we cannot understand yet. The origin of our universe, the story remains a mystery. Nevertheless, 138 billion years ago, the universe did indeed begin. Where is the hottest place in the universe? You might expect to find it at the center of a natural cataclysm, in a reactor. But even if you pass through its scorching depths and are utterly burned away, your journey will still be in vain. The temperature at the core of a star is only 15 million degrees Celsius. You may see more violent phenomena in the universe, such as explosive supernovae. During the dramatic death of stars, overheated gas can be thrown in all directions, many light years away, leaving behind a neutron star that has undergone gravitational compaction. Its central temperature far exceeds that of a normal star, reaching 100 billion degrees Celsius. But this is still not the highest temperature. In fact, in our vast universe, the highest temperature ever recorded is on the shore of Lake Loire in Switzerland, under the snow-covered ground 100 meters deep, and it is not from natural processes, but rather the joint effort of hundreds of scientists. And CERN, Large Hadron Collider, billions of euros in research and development at the Large Hadron Collider. Individual particles regularly at speeds close to the speed of light. Mutual collision. In 2012, 2 lead atoms collided. The temperature generated briefly reached about 5.5 trillion degrees Celsius, 50 times hotter than a supernova explosion. But this is still far from the highest possible temperature. Temperature is merely an expression of the energy movement or vibration speed of particles. Absolute zero marks 0 kelvins as the lowest limit. If possible, particles theoretically would completely stop moving. But there is also an upper limit, that is absolute temperature. It marks the highest temperature before the particle itself is torn apart by its own energy. It is called the Planck temperature, approximately 1.4 by 1312 Kelvin, named after this impossible scorching temperature. Max Planck is a German theoretical physicist. He made academic progress in the early 20th century. His ideas are considered the cornerstone of quantum physics and led to the quantization of light, breaking it down into discrete energy packets called photons. But they also made him consider other particles in nature, basic quantum, utilizing cosmic characteristics such as the speed of light and gravity. Combined with his Planck constant, he defined the Planck length as the minimum distance. Quantum light passes through this tiny distance in a vacuum. The time required is Planck time, equivalent to 5.39*10^-44 seconds. The Planck temperature is the actual measurement of absolute heat. It is the temperature at which the wavelength of thermal radiation reaches the Planck diameter. It cannot be any smaller. Say these numbers, beyond our true scope of understanding. This cannot fairly reflect the human brain. Throughout our evolutionary process, we have adapted to scales relevant to us. Therefore, these Planck units seem too small, or in the case of temperature, too large, with no practical use. But when considering the beginning of life, that immeasurable tiny moment, these units truly come into play. Because our universe is expanding, density is getting smaller and smaller. In all of its history, scientists do not know if our universe is infinite. But if it is, then it has always been this way. It doesn't start from a single point. It was also infinitely large at the beginning. It doesn't grow over time, but its density gets smaller. The observable universe is the only part of the universe we can see or interact with, affected by the speed of light. And since the birth of the universe 13.8 billion years ago, the limitation of the distance it can spread. But as we go back in time, the observable part of the universe will shrink and become more compact, until eventually we reach a time unit where only one Planck length exists, a diameter of one Planck length. Our observable universe is compressed into such a tiny space. The entire universe's temperature is exactly at the Planck temperature. Learn that at this moment in the universe, after the explosion, 1 in 10 billion, 1 in a trillion seconds is not strange. Therefore, the beginning of time and space is known as the Planck era. This was a very strange era in the universe. Everything we experience today is governed by certain unchangeable natural laws. These laws are ultimately governed by the interaction of four main forces. The strong force binds atoms together, the force that controls certain types of radiation. Electromagnetic force distributes energy over great distances, as well as gravity, just as Marx predicted in the late 19th century by Planck. Strong and electromagnetic forces can be quantified and are considered as individual interactions that are tiny, enveloping particles similar to matter. These so-called messenger particles are respectively called gluons, W and Z bosons and photons. But gravity is different from its general relativity. Albert Einstein overturned the classical mechanics definition of gravity. Instead, he conceptualized it as the curvature of space-time, distorting the structure of reality through various large-scale experiments. General relativity has been verified time and again. Space-time curvature caused by gravity, now considered an inherent property of the universe. It affects all matter and energy in the universe. In the Planck era, long before any traditional natural laws appeared, gravity is the first to manifest. But there is a problem. Everything we know today about gravity is based on Einstein's successful theory. But this theory in the Planck era, only on a larger scale, received true testing and validation. However, our entire observable universe, compressed into a region smaller than a proton by 1 trillion times, so general relativity doesn't really help. On the contrary, the extremely small dynamics are governed by quantum mechanics. At sufficiently small scales we can consider the individual subatomic particles of matter, or the quantized forms of force and energy. Particle, a completely different set of rules dominates. Nothing will appear in the position you expect. The act of observation itself will change the outcome. Quantum physicists consider probabilities. Nothing remains unchanged for long. Fortunately, this boundless quantum world, ruling only at the nanoscale. When we reach the more familiar scale, the probability monster has been averaged out. But in the common era of nanometers and Planck, quantum is inescapable. And here exists the problem of understanding how things work at that moment. General relativity and quantum mechanics, fundamentally incompatible. So researchers are still looking for a solution, namely the so-called quantum gravity. He is able to reconcile in modern physics the two most important theories and correctly describe the behavior of the universe in the Planck era. Unfortunately, considering the collider facilities, generating and researching other forces, the enormous energy required for messenger particles, as well as gravity, occupying a high plane and defining the entire spacetime. This problem cannot be reasonably solved through experimental means. A diameter is needed, approximately equivalent to a particle of our entire solar system. Accelerator. Only under extreme Planckian error conditions can enough energy be generated to truly detect gravity, but this does not hinder theoretical speculation and inference. An idea suggests, like other fundamental forces in nature, gravity is also transmitted through messenger particles. The quantum unit of gravity is called the graviton, but gravity is a much weaker force than the others, to the extent that its faint messenger is almost impossible to detect. Another theory called loop quantum gravity is entirely different. Physicists imagine that spacetime is smooth and constantly changing geometry will eventually pixelate at the smallest scale by using lines or rings instead of dotting. Restarting Einstein's general relativity equations, gravitational calculations at the quantum scale become easier to manage. Perhaps the most important quantum gravity solution will continue to thunder past. In the context of theoretical physics, string theory will traditional physics point particles. Imagine a one-dimensional vibrating string. The vibration state of the string defines what a particle is and what is the elusive gravity. However, in order for the mathematics of string theory to work, it is necessary to involve no fewer than 10 or 11 dimensions. Many of these dimensions will fold together or be split into two-dimensional or five-dimensional structures. About how quantum gravity actually works, every assumption is more puzzling than the last. These assumptions are rooted in the abstraction of mathematics, almost impossible to visualize. However, when we look back, imagine the first second of the universe in Planck's era. We try to do this, ironically, in the 1950s, when quantum mechanics science was still in its infancy. American theoretical physicist John Ockar Wheeler, it provided us with that period of turbulence and chaos, specific description of the conditions. He imagined the early universe was composed of a bubbling dynamic quantum foam. This quantum foam, as Wheeler described its appearance, it is because of the quantum scale, dynamic interactions and unpredictability. Heisenberg uncertainty principle seriously damaged us. Define the Planck-size universe. A little bit of time, the ability of length or energy. Therefore, the continuous and coherent spacetime we are familiar with today is inherent. Unpredictable and changing foamy textures take the place. This texture will change randomly. Quantum microblack holes and wormholes spontaneously appear. Then it vanished without a trace. In this high-energy super-universe, there is no obvious cause and effect. A compact and miniaturized universe. Everything is possible in the briefest of moments, but just after 1 billion trillion trillion 1/trillion seconds, the universal unpredictability of the Planck era ends because of the tiny expansion and cooling of the universe, signifying the arrival of a new era. The universe won't be like this again for a while, seems or appears like, but from now on, our current theory at least has the chance to describe what is happening. Everything in our universe, all are controlled and defined by the four fundamental forces of nature. Imagine, turn on your TV. Gravity keeps you firmly fixed in your chair. Keep the Earth's atmosphere close to the surface, and make the Earth revolve around our nearest star, to provide a habitable environment for your continued survival. Nevertheless, gravity is relatively weak. You can overcome it with the muscles of one arm. Lift the remote control. As a response to pressing the button, invisible infrared electromagnetic radiation, the beam emitted by the remote control passes through the living room scene, through millions of tiny pixels that emit visible light, vividly presented before your eyes. Visible light is another form of electromagnetic radiation. It passes through the room and reaches your eyes. Your eyeball itself is a miracle of evolutionary innovation, but they ultimately rely on electrons and atomic nuclei, properties and behaviors of inner atoms. They are bound together by electromagnetic forces. The atomic nucleus itself is bound together by strong nuclear forces. Protons and neutrons are forced to gather at the center of the atom. Not only that, these protons and neutrons, in fact, are combinations of three smaller subatomic particles, called quark. They are also bound by the same force. Together, every atom in your body, the very existence of what is on TV depends on this power. When your eyes focus, as you interact with the moving images on the screen before you, every nerve in your brain is emitted at a frequency as high as 200 times per second. All of these coordinated televisions, depend on the proper balance of potassium in the body. Like other elements, potassium is strongly bound together, but there are other factors at play. Because potassium's radioactivity is very weak, there are about 5,000 potassium atoms. A radioactive decay occurs every second. This decay is driven by the weak force. Therefore, 150 million kilometers away, the core of the Sun burns with the heat of a stellar furnace. This furnace converts hydrogen into helium. The heat generated by this extremely powerful reaction keeps Earth habitable on a galactic scale, comprising the Earth battery and all elements of yours. All also depend on the weak nuclear force. These four fundamental forces, gravity, electromagnetic force, strong and weak forces acting together, shaped our experience of the universe. Throughout the billions of years of cosmic history, most of the time has been like this. But at the very beginning, various conditions, a set of very different rules was jointly formulated. After the Datang era and the Planck era, only two forces exist. But how could it be like this? The key to visualizing it lies in flipping a coin. Flipping a coin to decide between two equally weighted options. One side with a head facing up, the other side is up. Only when the coin stabilizes after being thrown straight, when the thumb and index finger are bent, the energy generated is completely exhausted. When the coin comes to rest, only then can a decision be made. But before that, when the coin is still full of energy, when rotating in the air or on the table, it is even impossible to distinguish two faces. You have two choices, only one rotating sphere as self. All of his features. This is what we studied in basic forces. When acting at higher energy levels, the energy existing in the new universe causes the temperature to rise sharply. If the properties of both the strong and electromagnetic forces begin to weaken, they become blurred. We no longer see the different heads of the electromagnetic force and the weak tail. Instead, seeing the faceless force of the two rotating, the so-called electroweak force further increases energy. The concept of spinning a coin applies again to the strong and electroweak forces. At sufficiently high temperatures, the two become a unified dynamics. This process is called grand unification. This is the ultimate unification of the three main fundamental forces. The so-called strong force has emerged. Although this neatly spinning coin, grand unified theory, not yet experimentally proven, even if the energy collisions and particle accelerators can point us to the point of combination of electromagnetic and weak forces. A powerful force requires millions of times the energy to lose its identity, just as gravity, as the fourth fundamental force. Whether it will be accepted into a unified range, this is a mysterious and unpredictable. The problem of Planck error. It is also another problem of the competing theory of quantum gravity. The well-known grand unification theory is an explanation after the Planck era, a powerful competitor in the operation of the universe, in a time longer than the entire Planck era. Within 10 million times the duration, the expansion and cooling of the universe. But it proves how dense the universe was at the beginning. Even now, the entire observable universe is still smaller than a quark. The potential energy of the universe is compressed into such a tiny space, with a temperature reaching 100 million trillion kelvins, higher than the temperature that can be achieved by large hadron colliders, by several trillion times. These are the conditions of grand unification, by strange electron power, the era of chi, and the strange interactions it brings. A tiny universe, filled with particles experiencing extreme identity crises. Photons spontaneously transform into matter. Antimatter produces quarks and leptons. But these electron particles have extremely short lifespans. Just when the electron core is formed, bosons will only complicate matters, help quarks transform into leptons. Leptons transform into quarks. Matter transforms into antimatter. On the contrary, under the chaotic rules of unification, energy and matter are both free. Particles are both virtual and real. Until it starts after 1 in a quintillion seconds, the temperature drops to just 1,000 quintillion degrees, cooling it enough for the strong force to break free. Two forces become three. Everything changes again. But this picture has a problem. Although these theories may fully describe what happened after the Big Bang, the behavior of particles in the initial moments, but they could not explain the large-scale universe that ultimately exists. In fact, when the initial conditions, when compared to the ultimate result of the universe, the Big Bang seems to have been broken. By July 2022, the iconic James Webb Space Telescope will be stably operating in space. At a distance of 1.5 million kilometers from the Sun, he is finally ready to begin his scientific operations. But when he held up the 18 golden mirrors, focused on some of the deepest parts of the observable universe, when scientists saw the revolutionary telescope image returned, feeling shocked, American astrophysicist Allison Patrick wrote in the scientific journal Nature, he found himself lying in bed at 3 a.m., can't sleep, wondering if everything he did was wrong. Within a month, these images in Patrick's comments then took on their own life. A fixed speed of light means the deeper we go into space, the further back in time we go. Distance corresponds to the birth of all things. 2 billion years after birth, James Webb's Space Telescope seen galaxy. Not only that, the orderliness of these galaxies far exceeds people's imagination. The formation theory of stars and galaxies. This is inexplicable, and this is exactly what Kirkpatrick is very worried about. Unfortunately, soon his concerns were extended to the Big Bang itself. Some media claim that the Next Generation telescope, with its first photo, has overturned this landmark theory. Thank goodness, these concerns are unnecessary. Scary. Trick only cares about the existing theory of galaxy formation, rather than the creation of the entire universe, structures that early galaxies cannot explain. It means there is a missing piece in our understanding. It's not to say everything we know is wrong. It's just a storm in the universe teacup. So the Big Bang is at least not affected right now, but it completely explains how our modern universe was formed. It has always been subject to more severe threats. When we observe the large-scale structure of the universe today, many phenomena do not add up completely from the start. Although stars burn at temperatures of millions of degrees Celsius, while the vast space is above absolute zero, shivering at a few degrees of temperature. The average temperature observed in one direction, 2.7 in the universe than any other place. Kelvin is very similar. The diameter of the entire universe is 93 billion light years. But if the universe has been expanding for nearly 14 billion years, then how can 2 points more than 14 billion light years apart average out without breaking the speed of light? The fact that we now observe this thermal uniformity implies that there was thermal uniformity in the very first moments of the universe. Considering compactification, the nature of quantum fluctuations in the early universe, this fact seems extremely unlikely. It is known as the homogeneity problem or the world problem, but there is more. Einstein's general relativity describes how massive objects create curves in space-time, then controlling the movement and evolution of matter in space-time, the Milky Way galaxy and black holes, leaving dents and pockmarks in the local scale structure. But when we scale down to a larger range, these imperfections will disappear, leaving a smoother structure. Like the average temperature of the universe seems to change very little. On the largest scale, the universe appears to be flat. If the overall density of matter in the universe is sufficiently large, space-time will exhibit what is known as positive curvature, like the surface of a sphere bending backward. This means the gravitational pull exerted by all matter in the final universe will be enough to slow down and ultimately reverse the expansion trend, making the universe collapse backward in what is known as the Big Crunch. Conversely, if the overall density is much lower, it will lead to negative curvature of space-time, bend in an open manner, like the surface of a saddle. Under this geometry, gravity can never overcome expansion. The universe will forever expand. Which of these overall geometric shapes holds true? It has a significant impact on the evolution of our universe's future. Therefore, astronomers have been dedicated to measuring the overall curvature of the universe that we can see. Contrary to intuition, it seems to be completely flat. Like the world problem, the possibility of this happening is very small. It's like flipping a coin and having it land perfectly on the edge. The reason is obvious. This is known as the flatness problem. There is also an additional problem. Within the first 1/trillionth of a second, our theory of the universe was overturned. It seems there is no magnetic field at all in the entire universe. A dipole charge exists in the form of positive and negative pairs. They cancel each other out, forming a stable neutral charge hole. Similar magnets have north and south poles. Magnetic field lines flow between them, creating a stable balanced void. However, although positive and negative charges can be discovered individually, just like in isolated protons or electrons, but magnets do not have such isolated poles. No matter what we look for in the universe, we have not yet found an isolated monopole without an opposite pair. So one night in December 1979, when puzzled by the mystery of the missing Toshikazu, theoretical physicist Alan B. his thoughts reached an amazing solution, not only solving his own problem, but also solving the horizon and flatness problem. Instead of over billions of years, gradually expanding to the vastness we see today, Gus discovered a mechanism. Through this mechanism, the the universe can suddenly expand almost instantaneously to many times its original size, then slow down and continue expanding in a more linear way. The period of expansion proposed by Goose will make the universe within less than 1/trillion seconds expanded by about 90 times, thus generating exponential expansion. Fundamentally change the face of the universe, because when the exponent grows, things can become very large very quickly. Imagine folding a large piece of paper over and over again. If the initial thickness is 1/10 millimeter, then the first fold will double it to 2/10. The next fold makes its thickness slightly less than 0.5 millimeter. The third fold doubles it again. Now it's about the thickness of a fingernail. Not much so far, but when you fold it 7 times, a single piece of paper, now it has reached the thickness of the entire notebook. After folding 10 times, the thickness of the paper will be comparable to the width of the palm, and the actual world record for conducting this experiment. Only fold 12 times. In 2002, a female student from the United States folded a thin paper over 1.2 kilometers in length, folded into a bundle. The thickness exceeds 0.5 meter, but if it were possible to make and process larger paper, further folding would increase the thickness to astronomical numbers. After folding 23 times, the paper thickness will reach about 1 kilometer. After folding 30 times, the paper thickness will be enough to reach outer space, rising 100 kilometers from the Earth's surface. After folding 42 times, the paper's thickness will reach the moon. After folding 51 times, the paper's thickness will reach the sun. After folding 81 times, the width of the paper will be comparable to the Milky Way galaxy, approximately 141,000 astronomical units. After folding 90 times, is equivalent to 90 times the scale proposed during the period of ancient thinking expansion. It will turn this huge paper into a pear, folding paper larger than the entire Virgo supercluster, 13 million light-years. This incredible expansion is proposed by Alan Goose. In less than 1/trillionth of a second, the entire universe will expand. After going through the plan, the blank age and the chaos of the Daxing City era, turbulence, the incandescent ultra-dense universe expanded to over a billion times its original size. It is this expansion that caused the Big Bang. In an instant, the universe seems so hot, vibrant, and full, and now it has become vast, empty, and cold. Although this may seem extreme, but it is indeed the solution to the Big Bang Theory, an elegant solution to 3 difficult problems. Because of this expansion, we can accept the possibility that the vast universe we see, actually, it's not all. It's just a bubble of the observable universe. Its size is determined by the speed of light over the time that has passed, and determined by the expansion that has occurred since the beginning of time. Due to the expansion and the subsequent expansion, our observable bubble has a diameter of about 93 billion light-years, but it is still only a small part of the entire universe. Right in this invisible range we can find the answer to the problem of the world problem of thermal uniformity. Only when we see uniformity applicable to the entire universe, only then does it become a problem. But expansion allows the compact early universe to contain extreme thermal variations. These changes, then, they are far apart during the exponential expansion. The local region of the observable universe represents only a small part of the whole. Before the expansion occurred, the whole was in a state of thermal equilibrium. It is possible to be very different from the other parts we cannot see. The flatness problem in the same space-time region, only when the flatness we see applies to the entire universe. Is it a puzzling coincidence? But if we only see a small part of the whole, then it is impossible to say whether it is truly like that. This might be a perspective issue from the southeast direction. Just like the ocean, the world looks flat, but only when we fly above the surface and perceive more of the Earth can we see that it is actually curved. The broader universe may be positively curved, negatively curved, or a twisted combination of both, but we cannot see our own universe coastline, the absence of magnetic monopoles at last, only if we assume that they are missing throughout the universe. But if their number in the early universe, according to the predictions of our current model, then exponential expansion will cause them to be separated from each other until they are distributed throughout the observable universe, approximately 1. When we are within a sphere 930 billion light-years wide, searching for a strange monopole, it's no surprise that we haven't found it yet. Inflation now has become what we have for the universe. Early understanding is part of cosmologists since the revelation of Alan Cook. It has taken 40 years to figure it out. Clear, the universe can suddenly and violently explode. The time when this dramatic phase of the mechanism occurs, coinciding with a decrease in energy and cooling. This led to the grand unification of the fundamental forces and the emergence of strong and weak forces. Some scientists speculate that the decay of the precursor boson messenger particles of the Kaluza-Klein force, a powerful inflation field was created, carried by a new messenger called a bomb. This overwhelming new inflation, energy-driven cosmic exponential expansion, almost instantly appeared. Quantum scale irregularities expanded to large-scale structures. Shunt quantum long fall become a huge area with excessive density and energy. For galaxy clusters and superclusters in the modern universe, provide seeds. All of this inflation is inevitable, cooled and cleared the universe, causing the average energy level to drop by 1,000,000 times. But when it stopped, explosion field and particle decay, most of the energy is returned to the universe. This stage is called reheating. It is precisely this that makes the decisive creation of matter possible. Now in a larger and more spacious universe, the laws of nature are approaching what we can ultimately understand and model. This is called the electroweak era. It lasted for about 1/100 billion seconds after the Big Bang. Quarks and leptons, matter and antimatter, are all subject to gravity, dominating by the strong force and the merged electroweak force. But the temperature and energy are still too high. Strong cannot have any practical effect on the ultra-high energy particles of this post-inflation era. Similarly, the electroweak force on matter, there is almost no control over the interaction of energy. Although gravity may have existed throughout the universe since the birth of the universe, but it still lacks a major component. This makes gravity almost powerless until these newly formed particles acquire a certain mass. They are still difficult to control, need another energy decline and another cosmological transition before we can begin to recognize our own symmetry everywhere. In nature, we can see balance everywhere, patterns and geometric harmony, whether in our own bodies, still in the bodies of all animals. We are all bilaterally symmetrical, mirrored from the center. In those with the most perfect symmetry, feeling the greatest beauty. Many organisms also share bilateral symmetry with us, from the largest whale to the lowest worm. If not double mirroring, other animals, such as starfish and sea urchins, prefer pentameric mirror symmetry. Scientists have discovered evolution clearly favors these balanced symmetrical forms, especially because they can handle more complex situations than others, in non-repeating sets, simpler instruction construction. Moreover, it is the simplicity of mathematical algorithms. It is the foundation of symmetry in the natural non-living world. In science, the meaning of symmetry is far broader than its everyday usage. It indicates that something is the same. Something will never change no matter what happens. From the laws of physics to the laws of conservation of energy and momentum, the universe is clearly symmetric. Positive charges and negative charges maintain a balance. Some particles rotate clockwise, others rotate counterclockwise. If you measure Centaurus, the gravitational strength of Alpha Centauri, you will get the same results as our solar system. However, the universe is not completely symmetrical. Just like the human body, when observed closely, the heart leans to one side. The perfect balance of the universe also has flaws. Some particles will never rotate clockwise. Some particles never rotate counterclockwise. An imbalance in the quantity of matter and antimatter. An electric field can do what a magnetic field cannot. Although the two are theoretically equivalent, many of these imbalances are key to how reality operates. But in fact, cosmologists believe that around 1/100 billion seconds, he did not start in this way. Everything was perfectly symmetrical. There was balance, but with the final separation of force, the appearance of something, everything changed. This thing will affect most of existence. Like under temperature, it will signify the phase transition of water from steam to liquid, and then to solid ice. Each transformation fundamentally alters its nature and reduces its symmetry. Therefore, in the young universe, the temperature drop brought about a phase transition of energy and matter within it. As the four fundamental forces finally completely split and crystallized into independent entities, a new era has begun. The quark era is first defined by the interactions of matter. In our universe to date, the largest single object discovered, it may be the hypergiant USQT. Its diameter is about 1,700 times that of the Sun. If it were located at the center of the solar system, its outer edge will be located beyond Jupiter's orbit. But like all stars, he is almost entirely composed of some of the smallest things in the universe. Hydrogen elements, single hydrogen and helium atoms. Hydrogen is the smallest atom, while the atom itself was once thought to be the smallest thing. Their names come from the Greek word indivisible. But thanks to the revolution in atomic theory at the beginning of the 20th century, now we know that atoms are very easily split. This fact led to human history, the birth of some of the most destructive weapons. Hydrogen and helium are simple, though, but they are made of protons. Composite particle composed of neutrons and electrons can be relatively easily separated and manipulated. But even these are not the smallest fundamental particles. There are also protons and neutrons, themselves composed of smaller units as composite, called quarks. The various properties of quarks and the properties of electrons finally decided to include us beauty, the characteristics and behaviors of everything within, searching for the fundamental particles of matter. Always physicists, a guiding task for over 200 years, to break down smaller particles through experiments to reveal what's inside, requires a large amount of energy, and this energy, only through accelerating these particles to extremely high speeds. Then they collide with each other in particle collisions. Only then can we obtain, by examining the wreckage of these collisions, we can piece together a complete picture, the picture of the constituent elements of the universe. This picture has become the standard model of particle physics. Theoretically, it is enough to explain why everything in the current universe is this way. The normal matter we see, composed of protons and neutrons, they are collectively referred to as hadrons, but they themselves are composed of quarks. Each quark has unique properties. For example, the quality charge is self-selected, as well as another attribute called color. This is an arbitrary name. It has nothing to do with color, but it helps explain how they combine together. A positively charged proton, made up of 2 up quarks and 1 down quark, and a neutral neutron, made up of 2 down quarks and 1 up quark. But there are also other types of quarks. They have profound names, such as strange charm top and bottom. They combine together, forming more peculiar composite Helron particles. These particles outside of physical experiments have almost never been seen. Therefore, despite these experiments, where particles are crushed together with increasing force, physicists have found no evidence suggesting that quarks are made of any smaller matter. They seem to be really at the bottom of the rabbit hole. Meanwhile, surrounding the atom and the rotating electrons seem equally inseparable. They are particles known as leptons. Although all normal matter is composed of negatively charged electrons, but strange types can be found in alkali metals. Muon lepton, leptons and several neutrinos can all be found in the debris of particle collisions. So our standard model, composed of 12 basic indivisible particles, 6 types of quarks and 6 types of leptons. Additionally, there are antiparticles corresponding to each, and messenger particles of fundamental forces, photon of electromagnetic force, jot of strong nuclear force, W and Z bosons of weak nuclear force. If there exists a virtual particle transmitting gravity through spacetime, then it can still escape detection. So there are now only 4 types of gauge bosons, including matter particles, describe everything in the universe, at least almost everything today. So far, our models are all missing a key part, that is mathematics, quality from light to none. Every element in the universe has its own characteristics. Mass mainly corresponds to the number of protons and the neutrons inside the atomic nucleus. Therefore, most of the atom's mass comes from these protons and neutrons. But when we focus our gaze smaller and smaller, seeking the ultimate source of quality, what we see is not like this, because it turns out the weight of a proton is far greater than the sum of its parts. The basic particles of the proton core are 3 quarks, but their mass accounts for only 9% of the total mass of the proton. The rest comes from the energy stored within the atomic nucleus. This is according to Einstein, with his famous equation E equals mc squared, determining the intrinsic relationship between energy and mass, as well as the medium of the strong nuclear force according to Jiaozi, strange quantum interactions. So when we reconsider the universe, the mass of every normal substance, over 90% of the quality is real. In fact, it's not really from the material itself. Instead, it comes from the potential energy in gaps within matter. But quarks still have mass. This is something different from that energy. The reason has long been a mystery. Photons and gluons can survive well even without mass. Massive electrons and muons, even smaller than the smallest quarks, while carrying the weak force W bosons, 4,000 times heavier than a car, even heavier than an entire iron atom. So what caused this incredible mass difference? Why do particles have mass? This question has been troubling British theoretical physicist Peter Higgs 20th century 60s. He teaches and conducts research at the University of Edinburgh. To solve this problem, he proposed that all particles in the universe initially had no mass. At a moment in the first instant, a new energy field appeared and permeated the entire space-time, bestowing the property of mass on various particles. This Higgs field will be transmitted by its own quantized messenger particle, the Higgs boson. Higgs boson, to be listed alongside the other 16 particles of the Standard Model in describing the universe. Behavior and interaction of matter plays a vital role. However, despite the correctness of the Higgs theory, it took him nearly 50 years to finally find the elusive Higgs particle. Meanwhile, to support this expensive and seemingly esoteric search, the UK science minister promised in 1993 to buy a bottle of champagne. As the best analogy, explain the role and importance of the Higgs field to the public, although there are various suggestions, such as syrup pool prism and electric field. But ultimately, David is a physicist at University College London. Miller received the award. His description focused on a busy cocktail party. He said at this party, everyone was chatting happily. A normal person could relatively easily walk through the room. But when a more popular figure entered the room, they will attract the attention of party participants. Everyone wants to talk to them. Their progress in the room will slow down. Thus, the party participants in the room represented the Higgs field. And the popular figure is an example of something given mass for those who are too far away and cannot see the influential people. Rumors spread when people gather together to discuss their arrival. This physical fluctuation in the room flows among the crowd can be considered as messengers. Higgs boson, although this metaphor is not perfect, but he withstood the test of time, and time was ultimately proven to be frustrating. Looking for something akin to finding a needle in a haystack. What was needed? The two most powerful particles at the Fermi Laboratory in the United States, Accelerator, Chevron, and the Large Hadron Collider at CERN in Europe, crushing particles and searching for remnants for years. The problem is that although Peter Higgs has proposed the theory of fields and bosons exist, his theory does not explain what energy is needed to manifest. They also did not specify what would happen once the particle was found. What attributes will they have? This is like searching for a needle in a haystack. You don't even know what a needle looks like. Although ultimately in 2012, the Large Hadron Collider experiment achieved this seemingly impossible feat, scientists have confirmed that they have indeed found the Higgs boson, and in the process, proven the existence and role of the Higgs field. This particle won in the Standard Model, and the role of fields in the evolution of the early universe. After the Big Bang, 1/100 billion seconds, the catastrophic split of the electromagnetic force ended the perfect symmetry of the universe, because the W and B bosons carrying it decay into photons of the electromagnetic force, and W and C bosons of the weak nuclear force. But this is just the beginning of the breaking of symmetry. The Higgs field appeared around this time, injected in the process of inflation and electroweak splitting. Spontaneously generated real and virtual particles, W and C bosons, become heavy quarks and leptons, obtain mass according to their flavor and type, while photons and gluons continue as before. No quality, unbound by Higgs, as the quark era. After the Big Bang, 1/100,000 seconds fully realized, the universe eventually filled with all components, characteristic particles and characteristic forces, forming stars, planets, and our quark gluon plasma. The expanding universe is the primordial soup. All structures in the universe will form from this. Our universe is filled with incredible diversity. Some stars burn hot and fast. They explode catastrophically in less than 1,000,000 years, while other stars slowly sizzle. Countless planets exist unchanged for trillion years. A vast gaseous world, a scorched and barren rocky world. Occasionally, there are also green aquatic life worlds. On those worlds that exist with life like Earth, various life forms you can imagine, from tiny bacteria that breathe streams of air or methane, to self-awareness that builds buildings and telescopes. In the possibly infinite universe, in cognitive personnel, diversity is almost limitless, but some aspects of reality are unchanging, wherever you are in the universe. Or how do you observe them? These so-called natural constants have been revealed one after another, as scientists extend them time and again. We on the universe, understanding of behavior, we accidentally discovered seemingly magical numbers, unrelated to the speed of light. Any other physical laws or phenomena, in a vacuum, is generally considered the absolute speed of any object in the universe. Its limit is 299,792. 458 meters per second. There are also many other constraints, such as the energy of particles and their temperature, the magnetic field strength generated by current, as well as the electric field strength generated by charge. These constraints are not so obvious, but still very important. The masses of fundamental particles are also constant, but they seem arbitrary. This is a fact that even the Higgs mechanism cannot explain. So why are these natural relationships? Should there be these precise values? This question even confused the great physicist, Richard Feynman. he considered the so-called fine structure constant. It essentially describes the interaction between particles. Strength of electromagnetic force decided the possibility of electrons absorbing photons. Its value is slightly greater than 137, but it has no connection with any other physical law. There is no reason not to be 12,135 or 315. In fact, it is 137, rather than any other number. This is crucial for the overall state of the universe. If you are much larger or much smaller than now, you will severely affect the entire universe. The stability of protons. This means that matter will be very difficult to stay together. Most other natural constants are the same. If gravity is weaker than now, the universe will only be filled with increasingly thin hydrogen mass. If Tang were stronger, then all matter would be drawn into a black hole, or into violent short-lived stars, with no space-forming planets and life. Many constants in nature may seem arbitrary, but they are also finely tuned to suit the diverse universe we inhabit. But why do we still not know? This is just a lucky coincidence, or the mark of the Creator. Their hands are on the dial. Or as many scientists assume, our universe is merely one of many universes. All universes have different initial conditions and different fundamental constants. Value creation. The vast majority of poor universes led to failure. Only those universes with just the right value can cultivate universe diversity and longevity, thus cultivating us. Whatever the reason, this fine-tuning has already become very important within the first few seconds of existence. But a billion Big Bangs occur after 1 second. The universe is filled with an astonishing number of quarks, leptons and virtual particles, but the temperature and energy are still too high. These fundamental particles cannot undergo meaningful interactions. 1/1,000,000 seconds after the Big Bang, there are only 1 trillion in the universe. Botas and quarks finally slowed down, crazy shaking, allowing them to interact for the first time. As we can see, protons and neutrons are composite particles. Each particle is made up of 3 quarks, but the components of a proton are 2 up quarks and 1 down quark, not naturally sleeping together with different things. Up quarks are all positively charged. Like charges repel light charges. The closer they are, the stronger the mutual exclusivity. Therefore, the strongest force among all strong nuclear forces is needed, gathered together, mediated by gluons. Only then can they be combined together to form a stable hadron particle. But it turns out, the internal structure of the proton, even stranger than we imagined. Not only does most of the quality consist of energy, but quantum dynamics makes the composition of matter not as constant as we imagine. Sometimes one of the typical quarks inside a proton can spontaneously transform into a charm quark and its corresponding antiparticle of matter. This transformation is extremely brief. The charm quark will recombine quickly, but this means that protons are ultimately constantly changing. Normal quarks, called the mass quark, as well as the fuzzy mixture of gluons and bottom quarks, because both gluons and bottom quarks can be considered virtual particles. This means that the vast majority of protons, up to 99%, in fact, it is made up of non-existent particles. The internal working principle of protons and neutrons. It might indeed be very strange, but in the first 1/1,000,000 seconds after the universe's birth, they were becoming an increasingly prominent part of the universe's composition. However, due to this heat, the role of weak force in dense plasma, newly formed protons can easily change identity, becoming neutrons, and vice versa, only when the temperature of the universe further decreases. After approaching 1 second, does the special property of weak force begin to take effect. Protons and neutrons, eventually, in the so-called freezing process, slow down their transformation speed. Hadrons will permanently choose an identity. When this happens, seemingly arbitrary fine-tuning of natural constants, in this case, the masses of the up quark and down quark, are first, the real opportunity to shape the future of our universe. Because the down quark is heavier than the up quark, and a neutron contains 2 down quarks. The mass of a neutron, slightly larger than the proton containing 2 up quarks. Therefore, the final identity transformation occurs in a continuously cooling universe. From heavy neutron to light proton energy downhill slope, more energy-intensive holes in the opposite direction, more favored. It is precisely this very small quality difference, ultimately leading to in the universe, an imbalance in the number of protons and neutrons. Since then, about 1 neutron for every 7 protons. It turns out, this is an important ratio in the formation of the universe. Protons are the basis of hydrogen and helium. They are the fuel for stars, and also all other heavy elements in the universe. Component parts. These charged particles are the reason for the wind of neutral particles. Element interactions, thus leading to chemistry and biology. If things had started differently, if during the process of fine-tuning reality, intentionally assigning slightly lower quality to the lower, so the universe we see today will be very different. If the weight of a neutron is less than that of a proton, then during the freezing process, neutrons will have more than protons. Uncharged neutrons. The reasonable completion of chemical reactions is limited. Hydrogen consists only of protons, no neutrons involved. It will not stabilize in the long term. Some heavier protons can be preserved by combining with neutrons. Then it decays to form helium atoms. But helium, it is generally considered the most inert of all elements. It is essentially stable, but unwilling to be like this stable, in between excessive neutrons that do not react normally. Reaction occurred. It's hard to imagine how nuclear fusion works. We will be left with a cold and dark universe, without stars, without galaxies, without planets. Of course, there were no us either. Therefore we can thank the universe, whimsically inclined towards protons, instead of neutrons. But this is not the universe, the only imbalance formed in the process of evolution. There also exists a mysterious yet fortunate lack of antimatter. One day in the future, when we gaze at the sky, we might see an extraterrestrial civilization self-destructing. At the right time and in the right corner. This is almost no better than one of the darkest stars in the darkest part of the darkness. The subtle increments are more dramatic, but represent the energy explosion of a powerful weapon, sufficient to level the entire world. History tells us about division and misfit, a common theme of global civilization. There is no reason to believe this situation will not occur elsewhere in the Milky Way. Therefore, a war with extraterrestrial worlds is like Earth, where the efforts made to defeat the enemy are leading from pointed to explosive projectiles. The arms race, the struggle for the most destructive weapons, is still ongoing, but these advanced aliens are still not satisfied. Soon their attention turned to a more powerful, potential energy source. Their technological capabilities surpass those of humans. They have learned to produce and separate antimatter particles, suspended in a vacuum using electromagnetic force, until they are deployed. But they don't need a lot of fuel, or any form of launcher, because when antimatter comes into contact with normal matter from their homeland, the particles annihilate together. Self-destruction, releasing enormous energy. The energy released by just 1 gram of antimatter is equivalent to a traditional nuclear weapon. It requires about 90 kilograms of fuel. As the arms race progresses, stocks continue to increase, whether out of angry chaos, still just an accident. The explosion of this antimatter weapon can turn the night into day instantly. Blazing winds, destruction of the war factions, and all other life on Earth, the entire world, will change in the coming centuries. This is the destructive antimatter, the possibility of contact with matter. However, we are surrounded by it every day. 1928. British physicist Paul Dirac first predicted the existence of antimatter. He devoted himself to combining Einstein's special relativity with the relatively new quantum mechanics. He realized his equation not only applies to electrons with negative charge, but also to electrons with positive charge, thus predicting a completely new particle for science. That is the anti-electron or positron. 4 years later, an independent American physicist Carl Anderson, exploring in a crude instrument called the cloud chamber, detected this elusive particle. As the existence of antimatter is confirmed, physicists turn their attention to others. Antimatter particles. The 1950s, the California Proton Accelerator successfully detected the first antiproton and the first antineutron. 1995, scientists finally assembled an anti-hydrogen atom. Now we are from supernovae and black hole jets to fake radioactive decay, etc. In all kinds of environments, have recognized antimatter. In intersection, a positron is produced approximately every 75 minutes. Therefore, antimatter may not be limited to future science fiction scenarios, but based on the obvious lack of annihilation characteristics, it is still far less than normal matter in the universe. Physicists believe in every trillion particles of matter in the Milky Way, at most only 1 antiparticle. This is also good, because if the number of the 2 particles is equal, then annihilation will lead to the final destruction of all particles. Nothing can form stars and planets. But how did this fortunate imbalance occur? This issue still troubles physicists. Could this be another quirk of fine-tuning? At the beginning, antimatter would form alongside matter. Within 1/100,000 seconds after the birth of the universe, particle pairs were formed by spontaneous energy conversion. But in such a dense environment, they would soon encounter their opposites, together annihilate and transform back into energy. This self-generated and destructive process continues until the density of the universe decreases, without new quark, antiquark, or antilepton production. But gluons cannot distinguish the type of matter they assemble. When protons and neutrons are first produced, they will be accompanied by equal amounts of antiprotons and antineutrons. Everything should be in a balanced state. At this time, the amount of matter and antimatter should be without difference, because the behavior of these two particles is the same, and also only in pairs to be destroyed. Therefore, the number of each particle should continue to be equal. But this is not what we see. At 1/1,000,000 seconds of the universe timeline, at some point between 2 minutes, the balance between antimatter and matter changes, until only one antimatter particle remains out of 1/100,000. Until today, physicists are still unsure why this is the case. This may be partly due to, with Chen-Wu's weak experiments in the 1950s, the symmetry breaking caused by the appearance of its appearance. Experiments show quarks and antiquarks are actually slightly different. According to natural laws, this difference is very small, but enough for us to see. Even so, scientists believe this is not enough to explain the early universe, the overwhelming victory of matter over antimatter. On the contrary, they believe in another one that has not yet been discovered, and possibly extinct particles can play a role. This idea comes from what was found in the Standard Model, another asymmetry. Every particle and antiparticle we have found exists in both right-handed and left-handed forms, representing a type of chiral symmetry. Physicists call it parity, but there is an exception. Parity symmetry seems to be broken. Experimental physicists can only find left-handed neutrinos, and all antineutrinos are right-handed. Then, where are the right-handed neutrinos and left-handed antineutrinos? Scientists speculate they might have existed in the first 1/1,000,000 seconds after the birth of the universe, but they are unstable. If they decay preferentially into matter instead of antimatter, then this may have laid the foundation for the ultimate victory of matter. This theory is very appealing, but unfortunately, before we have a deeper understanding of these mysterious disappearances of neutrinos, we cannot do much to make this clear, and it will take until 1 second after the universe was born before neutrinos tell us anything. When we gaze into the deepest part of the night sky, we will see wonders at almost every wavelength. There are delicate, spiral galaxies, colorful nebulae, and dazzling points of light, called the stone star, distant supermassive black holes, devouring matter and light from the center of galaxies. But these stone stars still illuminate another peculiar feature scattered across deep space, called the Lyman alpha forest. Light passes through the expanding vacuum of space at a constant speed. The farther the object, its age also increases. So when we see stars from a distant place, what we see is how they looked billions of years ago. The light they emit is redshifted, extending to the red part of the electromagnetic spectrum, compared to how they usually appear. But when we examine these distant and ancient, solid spectral features, we can see, not only them, redshift light emitted under shorter wavelengths, there's also a sharp drop in the light we see. Sometimes they are very numerous, to the point where they gather together, just like on one side of the Alps, dense tall pine groves. This is the Lyman alpha forest. It is not made of trees, but rather by low-density hydrogen gas lurking in interstellar space, made of clouds, because when light passes through high clouds, some of it will be absorbed, causing the spectrum to decrease. It is ultimately intercepted by our Earth. This is what happens with the light from afar. What happened with the old-fashionable light? Every drop in the spectrum corresponds to the light clouds that were originally invisible. Visualize these fragile structures. This alone is already striking, but from the structure of this spectral forest, we can see more. Astronomers have noticed that absorption will gather at high redshift to the densest, which corresponds to the Great Era. This allows us to gain a deeper understanding compared to today. The earliest chemical and composition of the universe, early space was filled with these low-density cloudy clouds, so high that starlight could not avoid it. They are precisely the nursery for stars and galaxies that has prepared. He himself is the seed from the beginning of the universe's birth, his existence in the history of the universe. Many things happened in the course of 1 second passing, now only 110 degrees Celsius. It is filled with merciless particles, the victor of battle, and the energy from countless encounters of mutual destruction. Photons single through the quirks of the properties of the remaining particles. The balance between protons and neutrons is set, because spontaneous. The era of the birth and exchange of particles has finally ended. Particles with mass already have mass today. This is thanks to the Higgs field and its dominance, the four forces we live with today. strong nuclear force and electromagnetic force, weak nuclear force and gravity, currently in a complete and understandable operation. So far, in just 1 second, the operation of the universe is primarily in the field of theoretical physics. Our most powerful instruments are still working hard to produce various forms of energy, dominant in the initial moments. But now we have entered into a cosmic era. Experimental physicists, even astronomers, it can be studied in a more meaningful way. We have finally reached a part of cosmic history. We hope to be able to observe it, or even draw it, on the frigid wilderness of Antarctica. How many weeks of the year does the sun not set? This is where the work begins. January 2005. Scientists spray hot water directly into the ice sheet. At the cutting-edge ice cube, scientists working at the Neutrino Observatory began the arduous 58-hour manufacturing process to create the first 2.5-kilometer hole. This is one of the 80 holes. Now it is an ice cube array. Various holes occupy 1 square kilometer of the Antarctic ice sheet, but this huge size and incredible location, it's not this next-generation telescope. The only surprising feature, because it's not pointing at the night sky, is gazing at the Earth's interior. It has no lenses, mirrors, or radio antennas. Instead, it is composed of more than 4,000 modules, hanging on over 80 thin threads, in the deep of an ice cave, like pearls, hanging in the deep cold and dark of Antarctica. This might seem counterintuitive. In fact, this is the most elusive observation of the entire universe. An example of this, the ideal building ice cube Neutrino Observatory, below the world's largest lake, the bottom of the deep gold mine, combined with similar projects in the center of Japanese mountains. All of these are dedicated to searching for mysterious new types of neutrinos. As a particle, neutrinos were first proposed in the 1930s. At that time, particle physicists were balancing in decaying equations. Observation: neutrons sometimes spontaneously decay into protons and electrons. Wolfgang Giancarlo Pontriagen noted that a small amount of energy was lost. He assumed this was another type of particle, too small, as light as a ghost. There is absolutely no hope of detecting it. In fact, with the frequency of this nuclear decay, there are definitely 1 trillion ghost particles like this every second, flows through our bodies, and we had no idea at all. But scientists do not easily accept failure. 1951, American physicist Clyde Cohen and Frederick Raynes began searching for this ghost particle in what was later called the Goofy Project. They utilize a powerful nuclear fission reaction to provide the large amount of energy needed for neutrino detection. Cohen and Raynes first proposed to detonate a 20-kiloton nuclear warhead, and at a distance from the explosion, a massive detector installed just 50 meters away. This detector, nicknamed El Monster, was designed, used to receive flashes after new neutrino collisions. If it is built, it will ultimately be 1,000 times larger than any previous detector. However, this experiment has proven to be too challenging. Scientists turned to nuclear reactors for more controllable energy release. Therefore, in 1956, Cohen and Raynes' experiment finally succeeded, achieved what seemed like an impossible task, detected the ghost that has puzzled physics for over 20 years. Particles now, detection and research on neutrinos. Great progress has been made. Scientists can now produce and study them in powerful particle accelerators, despite still having, like the lake bottom neutrino detector, such massive detectors. Neutrinos can not only be used to answer questions about our universe today, it can also answer his original question. Neutrinos are produced by so many electromagnetic sources. Scientists are trying to use them. Let's study some of the most extreme events in the modern universe. 168,000 years ago, a star within a large black cloud had a supernova explosion. Fragments of the atomic bomb travel at speeds close to the speed of light through interstellar space. In 1987, including countless neutrinos emitted during the explosion, these fragments hit the Earth. Japanese scientists believe they are very lucky to detect 11 of them. Although this seems insignificant, but astronomers can use this neutrino lens. Seeing a supernova helps to usher in a new era of multi-messenger astronomy. Gravitational wave telescope, various electronics, frequencies and neutrinos can be deployed together to study and understand the most extreme in the universe and the most mysterious event. But that's not all. Neutrinos give us the opportunity to detect those too opaque for light to penetrate objects, because they are extremely unwilling to interact with any matter, so they can pass through everything from nebulae to stars, even entire planets. This is because They only interact with two fundamental forces, namely the weak force and gravity. This extraordinary penetration ability make them become a powerful tool for probing the earliest moments of the universe, determine the formation of matter about 1 second after the Big Bang, the absolute density of hot energetic particles and photons after, make the early universe completely opaque for hundreds of thousands of years. Our telescope relies on photons passing through empty space, cannot detect this opaque plasma. Therefore, to observe the past earlier, scientists need to adopt different methods. Neutrinos and antineutrinos are just part of the cosmic soup. They collide and scatter and interact with other matter because everything in the still dense universe is so full of vitality. But at about the 1 second mark, the temperature in the universe dropped to 10 billion degrees Celsius. The corresponding particles slowed down. Eventually their movement speed was slow enough. Neutrinos can escape and find roaring paths through other particles. They no longer collide with matter or the liquid of life. Therefore, they can break free to leave their imprints in the universe. So if we can find the imprints called the cosmic neutrino background by scientists, it will represent the image of the universe from just 1 second ago. Our astronomical range dates back to about 380,000 years. But if these remnants from the first second of the universe contain neutrinos, then they are more elusive than high-energy neutrinos. With every cubic centimeter of space, compared to 100 billion high-energy neutrinos, it is believed that there were only 300 from the very beginning. To directly detect them, we need to establish the precision of our instruments, 100 billion times more than now, or in some way, detecting the impact on the universe when they break free. Because as the first batch to pass through, the things that were originally opaque in the universe, these tiny particles are expected to leave behind in their wake. Microblast fundamentally change the distribution of matter and energy. Due to this destruction, certain parts of space will become slightly warmer, some parts will become slightly colder. In this 13.8 billion years, space has expanded. These patches magnified to larger scale structures in the universe. If we could decode some large scale structures written into the distribution of galaxies today, then we might be able to hear echo of the Big Bang 1 second ago. This is not the only one modern enigma that may originate from the Big Bang 1 second ago. This is the Tunguska event 618, about 1.82 billion light years away from us. Its luminosity is 14 trillion times that of the Sun, making it one of the brightest objects known in the universe. It is said to have a history of nearly 11 billion years. Despite its incredible luminosity, it is actually one of the largest black holes in the universe. According to reports, it is a supermassive black hole located at the center of the Milky Way. Its brightness, countless trillions far beyond the center of the Milky Way. The mass of 618 is approximately 66 billion times that of the Sun, more than 15,000 times the mass of the star HR 8799, the black hole at the center of the Milky Way. In fact, this black hole is even heavier than the sum of all stars in the Milky Way. Matter falls into it at a speed of over 10,000 kilometers per second, causing intense heating. Therefore, although the dark core at the center is devouring light, the matter within its attack radius, destined to be destroyed, still emits a bright glow. Carbon 618 might be the largest black hole we have ever discovered, but it is definitely not the only one lurking at the center of the galaxy of this kind of titan, a supermassive black hole with a mass over 100,000 times that of the Sun. It is a common feature of large galaxies. It is considered to have a significant impact on the way these galaxies evolve. After billions of years of formation and evolution, these fiery, massive hearts themselves, considered to be obtained by consuming from the Milky Way, growing with the stellar material of the accompanying personnel. But the formation of these supermassive black holes is a bit off in terms of timing. Astronomers have discovered this while surveying the sky, that these massive black holes formed after the Big Bang, being only a few million years, despite our model not allowing enough stars to be born and die to feed these early giants. We have discovered some supermassive black holes, less than a billion years after the formation of the universe, grew to 11 times the mass of the Sun, and according to the star formation model, only a black hole with a mass of about 100,000 times that of the Sun could potentially form. The potential solution to this puzzle might be found in a theory. The theory is based on our realization of the extremely large, many years before the appearance of the earliest supermassive black holes, regarding the developed 1971 Stephen Hawking proposed, the formation of black holes also has another way. It doesn't require any precursor star at all, but rather comes from density fluctuations in the early universe. He called them radiation-dominated era original black hole. At that time, the universe, still a composition of photons and matter, high-energy plasma, great unevenness, essentially lumps of matter. This is due to the expansion of quantum irregularities in the new universe, and the subsequent reheating caused. The inherent gravity in the universe will act on these density contrasts, leading to the entire early universe, large-scale gas collapse. However, after the Big Bang, there's only about a 1-second time window before the universe begins to expand and cool to such a size that gravity can no longer effectively pull matter into these black hole prisons. After that, the universe will have to wait millions of years, can form a new black hole after a star's death. But these original black holes may be the seeds of the black holes that we detect today and were originally unexplainable. The problem is that although this theory seems to be consistent with our understanding of the behavior of matter in the early universe, but we don't know exactly when they formed, as well as within their 1-second time window. How tall can it grow? No, very little. Mathematically speaking, the later an original black hole forms, the larger it is. Therefore, there is a huge difference in the estimated sizes of them, from weighing 100,000 pounds to the minuscule specifications equivalent to the weight of a paperclip, to a mammoth 100,000 times heavier than our sun. Then if they do indeed exist, how do we find and identify them? 1970s. Stephen Hawking also proposed, black holes are not just swallowing matter and constantly growing. He also proposed, black holes may possibly emit through what is known as Hawking radiation, reduce some weight. The smaller the black hole, the faster the weight loss. The uncontrolled acceleration of radiation will ultimately lead to a black hole being destroyed in an explosion equivalent to 1 trillion tons of hydrogen bombs. Any black hole with a mass less than 100 billion kilograms may decay within the age of the universe. Therefore, scientists have already begun using space gamma rays, telescopes and other instruments, looking for these characteristic explosive deaths, seeking these elusive primal seeds. Other potential methods, including searching for a black hole passing in front, microlensing and magnification of stars and galaxies, or try probing the original gravity well, the destruction of captured dense stars. But so far, all the achievements obtained from these researches have only ruled out certain size ranges, while the size of the original black hole, the possibility of formation, is becoming smaller and smaller. Although astronomers have not given up hope, the next generation of high-tech telescopes will continue to achieve a better range and accuracy than ever before. Performing a search, laser interferometer, space antenna LISA will be launched in the next decade, continuing to cross space in search of gravitational waves. Some of them may come directly from the original black hole. These black holes since December 5, 2022, at Lawrence, Livermore, inside the National Ignition Facility at the Morley National Laboratory. Since its formation, it has been wandering in the universe. Scientists at the laboratory focus 192 laser beams on a golden cylinder 1 centimeter long. Inside the cylinder is a fuel sphere the size of a peppercorn, containing 2 isotopes of hydrogen and uranium. When laser energy hits the spacecraft wall, heated to about 3 million degrees Celsius, higher than the surface of the sun, causing them to emit X-rays within the cylindrical chamber. These powerful X-rays then bombard the surface of the ingot, compressing the fuel at a speed of 400 kilometers per second. The fuel implodes in less than 1/100,000 seconds, reaching 1 billion times atmospheric pressure. Atoms in the riverbed fuse together, converting them into helium, while releasing high-energy neutrinos and other energy. A total of 2.05 terajoules of energy entered the cylinder, produced by fusion reactions in the past 70 years. This is 3.15 terajoules, for the first time by scientists, initiated a productive nuclear fusion reaction. Fusion itself is not exactly new. Humans have been creating lethal fusion weapons since the 1950s. In this reaction of 2022, it was the first time we created something capable of releasing more energy than the energy invested at startup. Approximately 50% energy gain is enough to boil 20 kettles. But this breakthrough for nuclear physics is still a major breakthrough. This process has already naturally occurred at the center of every star in the universe for billions of years. Not only that, if this huge change is resolved within the first minute, the physics of the universe will change. Humans have always focused on turning something into something else. the seemingly magical behavior of transforming into something else, whether it's producing flowers from thin air or alchemically turning base metal into valuable gold. There is nothing more than from ordinary things. The idea of obtaining new things, even more captivating, in the early universe was filled with such transformations and the unstable fundamental forces driving chaotic identity exchange. But this transformation continues around us. Even in the modern universe, radioactive decay mediated by weak force will cause nuclear fission and fragmentation. Thus, transmuting elements on regular and predictable timescales transform into smaller nuclei. This nuclear transformation occurs from carbon used to detect years 14 to 99 used for medical imaging by 235. Various elements used as fuel in nuclear reactors. This radioactive decay occurs due to the instability of the atomic nucleus and typically occurs spontaneously under the most environmental conditions. But as another form of nuclear transformation, nuclear fusion will see the atomic nucleus increase its mass and move up in the periodic table. Therefore, it is difficult to achieve. The identity of all atoms is determined by the number of protons and neutrons in their nuclei. Hydrogen has one proton. Different isotopes of the same element have different masses with a different number of neutrons. Chlorine has only one proton. Uranium has an extra neutron, double the relative mass of the atom. Uranium has 2 neutrons. Make the total relative mass reach 3. Only by adding another proton, the identity of the element will change. 2 protons form a helium nucleus. Among them, helium-3 has 1 neutron. The most stable helium-4 has 2 neutrons. Strong nuclear force. It is what holds all hadrons together to form stable atomic nuclei. But because protons share the same positive charge, they repel each other. Long before they were combined, they were pushed apart by another of the 4 fundamental forces, the electromagnetic force. Therefore, strong heat and physical pressure are required. For example, at the center of a star or inside a golden capsule radiating, discovered heat and physical pressure push the proton close enough to overcome with strong force. Its principle is that elements fuse into something new, forming heavier elements. Combining dozens of protons together need more extreme cosmic events, like supernovae or star mergers. Although they are difficult to replicate in the laboratory, scientists on nuclear fusion have a good understanding of how to work in a stellar furnace, create new elements from simple hydrogen and helium. They even witnessed and understood what is called failure inside the stars. The beginning of this process. Brown dwarfs are giant balls of gas, larger than Jupiter-like gas giant planets, but smaller than active stars. The heat and pressure inside are simply not enough to make hydrogen. Proteins hydrogenate into helium. The process is completed by using a heavier knife as an intermediate. However, these processes cannot explain where did the larger knives and helium atoms come from. Therefore, we need to look back to the era before stellar fusion. About 1 microsecond after the Big Bang, the average temperature of the universe at that time fell to about 10 million degrees Celsius. That is, in the first minute of the universe's birth, it finally cooled down to the point where quarks could combine to form protons and neutrons, becoming the foundation of all elements. But it was still far from the first stars beginning to shine. 1 billion years left, and the light of these stars is from the atomic nucleus, powering its nuclear fusion. Then when were these atomic nuclei, and how do they combine together? 1948. American genius doctoral student Ralph Alpha, with his mentor George Gamow. Cooperation, a mechanism that was later known as Big Bang nucleosynthesis, was proposed. It is a bold and inspiring theory, but the brilliance of Alpha's work, to some extent, it has been obscured. Gamow insisted in their groundbreaking paper join another author who did not participate in the paper development. In his words, the Greek alphabet seems unsuitable to have only Alpha and Gamow sign this article. So when preparing the typescript, added the name of Dr. Hans Bethe. Thus Alpha, Beta. Gamow's paper became the authority on the giant changes before the stars. Still do not understand the high temperature of the early universe, how hydrogen is converted to helium through the intermediate of a knife. Laid the foundation. Proteins are the lightest form of hydrogen, composed of a single proton. So once quarks combine to form protons, these hydrogen nuclei will exist. It should be noted that, about 10 seconds after the Big Bang, neutral-charged hydrogen atoms will form, carrying both protons and electrons. Temperature is low enough. Some high atomic nuclei can form, with only 1 proton and 1 neutron. But in this hot cosmic soup, temperature and particle energy are still very high, to the point where high atomic nuclei are unstable if they are hit by photons. At such densities, this is inevitable. These first ones that fit the atomic nucleus will split again. Physicists call this the blade bottleneck. Before overcoming it, nuclear synthesis can never be surpassed. The fusion of a proton and a neutron. It will only take another 300 seconds for the temperature to drop to, sufficient to make the blade more stable and form other elements. The first blade with a proton and a neutron can withstand the powerful compressive force throughout the universe by fusing with a single proton. Result: for the first time, a completely new stable element helium-3 was produced. From this point on, the next cosmic creation is more common helium. Helium-4 is composed of 2 protons and 2 neutrons. The helium-4 nucleus represents the most stable existing nucleus, and it is the hardest to split of all elements. For this reason, in the first few hundred seconds, most of the free protons in the early universe were swallowed by the Higgs. Cannot go any further, based on the initial balance of protons and neutrons, as well as the available energy at this time. It predicts that this will result in the universe's mass being approximately 25% of E. And this is indeed what we have discovered. Even 13.8 billion years after this helium energy burst, even after the birth and death of countless stars, there is still about 23% of helium in the universe. This single observation is enough to astonishingly confirm the alpha theory. It is here that we see the accidental fine-tuning of the universe's initial conditions. Another example, we already know. If the ratio of protons to neutrons is different than most of the ordinary matter in the universe, it will decay into uncharged neutrons and helium. But even if there's a proton-neutron ratio, if the matter in the universe in the Big Bang more compact during nucleosynthesis, then more helium would form. The non-reactivity of the universe, mainly composed of nuclei, means there are almost no chemical reactions. After that, it again becomes possible that the universe may have no stars, no galaxies, no dim prospects for our human race. Fortunately, it's not the case. Even so, more hadrons stably enter its stable helium nucleus. The universe is still full of potential energy, can be used for further dramatic changes. The current competition is to see in the universe ring, before the ambient energy finally drops too far, how many new elements can be created. After about 1,200 seconds of intense cosmic nucleosynthesis, the age of the universe is just over 20 minutes. The nuclear furnace finally emits a hiss and dies out. By human standards, it is still very hot, but it is too cold. No further atomic nuclei can form. At this point, only 4 elements exist: hydrogen, helium, lithium, and beryllium. Due to the brief stability of these primordial nuclei, only the first 3 can survive for sufficiently long times to see the first star and become the final fuel for creating the other 98 elements. These elements can be naturally found in the modern universe. At this stage, there are 12 hydrogen nuclei, each helium nucleus, and each of the 11 photons of the composite material particle. But with these basic components, the formation of everything else is truly ready. Even in 2022, scientists in California fused rivers. The rivers themselves, also 1.38 billion years ago, first formed in the high temperature of the newborn universe. Life in the universe is a chemical miracle. As far as we know, chemical miracles only occur in one place, on an unassuming, damp rocky planet, orbiting an ordinary yellow star, situated in one of the smaller spiral arms of the Milky Way. The endogenous, but despite the healthy fossil record, can be traced back to the history of the Earth about 3 billion years ago. How did life come to Earth? The moment of the origin of life. The spark of life fades in the mist of time. Biologists unanimously agree that life is carbon-based, oxygen and hydrogen-composed organic molecules composed of. Additionally, they found that all living organisms exist in the form of DNA and RNA, share a common chemical specification. DNA and RNA themselves consists of repeating units called nucleobases, cytosine, guanine, adenine, thymine, and uracil. A universal language is provided to encode information about how leaves grow, their stipules or hair follicles. But where did these molecules come from originally? Some people imagine, on the newly formed Earth, a warm and powerful chemical environment for assembling organic molecules and nucleobases from scratch provided perfect conditions. But there is another theory that suggests the components of life were not created on Earth, but between the stars in the deep of space. In fact, we are searching for convincing evidence of life matter in the distant universe. In 1969 in West Virginia, the Green Bank National Radio Astronomy Observatory, American astronomers at work, have detected the characteristic vibrations of formaldehyde molecules containing carbon, hydrogen, and oxygen in the deep interstellar space. Subsequent scientists have now discovered over 250 organic molecules in interstellar clouds and in the shells of matter around stars, includes alkyd and amine. All of these are latent in the range of lifeless universe, basic components of larger life molecules. This is another more convincing clue. As early as 8 p.m. in 1864, the potential of outer space to harbor life had already reached Earth. May 14th, a meteorite fell to Earth. It broke into 20 pieces near the town of Allier in southern France. Scientists who recovered and analyzed the Allier meteorite reported that its composition is very similar to that of the Pitts meteorite. This triggered discussions about this organic matter. Is it possible to come from a biological source? The fierce debate, but due to the lack of any identifiable biological structures, it is unlikely to draw such a conclusion. However, nearly a century later, using more modern instruments and techniques, reanalyzing this meteorite, chemists were surprised to discover the nucleotide molecules of the line ticket order and the bird ticket order, which are the same as those in our DNA today, the same as the molecules found in RNA. Subsequently, regarding those that fell around the world, studies on other meteorites rich in organic matter discovered the nucleotide bases of other parts of Earth life and other items not found in our biological composition. The clear answer to this fundamental question has not yet been revealed, but the observation results so far at least points to one certainty. That is an astonishing fact about the universe. Without any special stimulus or encouragement, the universe itself has the ability to build molecules and undergo extraordinary chemical reactions. This spatial chemistry, the organic universe, originated in infancy, less than 100,000 years after the beginning of time. During the Big Bang nucleosynthesis process, the violent behavior of element creation stopped just 20 minutes after the universe existed. Because of the universe's expansion and cooling, environmental energy is no longer high enough to provide fuel for nuclear fusion, but the conditions are still extreme. The entire universe, still denser than the air we breathe, the temperature is still too high, the speed of the hydrogen electron, not enough to be captured by newly formed elements. Energy in the universe is still surplus. Matter exists in the form of thermal separation, as plasma. It will take tens of thousands of years to cool down further. Let everything begin to change. Helium hydride is an unstable helium ion combined with hydrogen. It is rarely found in nature. 1978, John, an astrophysicist at the University of Minnesota, Black proposed it can exist in large quantities in space, especially formed in planetary nebulae. He predicted, in the energy explosion of the late life phase of red giants, around the neutral light clouds, there will be a thin layer of ionized plasma. In this environment, helium ions are strong. They need electrons to neutralize their charge. This may drive them to steal an electron from the only other source around hydrogen. The combination of these two in an overheated nebula will ultimately lead to the formation of helium hydride ions. However, this molecule remains elusive. Subsequent long-term searches yielded little success until 2019. An innovative telescope successfully achieved what seemed impossible. Now, most telescopes are either located on mountaintops on the ground to avoid the most severe light pollution, weather and atmospheric distortion, either be launched into space to get rid of these problems, because they orbit the Earth or the Sun together. But the Sophia Observatory did something different. It consists of a mirror telescope that is 2.7 meters wide. This telescope points at the rear door of a specially modified Boeing 747, flying at an altitude of 43,000 feet in the sky. In this highly instrument connected to the telescope can enjoy many benefits of the space telescope, because they will be elevated into most of the Earth's atmosphere water. Their height allows them to detect water vapor, typically absorbed light wavelength. It is crucial. Telescope connected to the far infrared receiver. Its abbreviation is GREAT, with sufficient resolution. Ultimately, it can identify weak overlapping states in deep space. Hydrogen ion signal. The final discovery. From 3 days of observation of the planetary nebula NGC 7027, the nebula is about 3,000 light-years from Earth, located in the direction of Cygnus. In this hot and vibrant interstellar environment, just as John Black predicted 40 years ago, helium hydrogen can form and leave its characteristics on the nebula. The spectrum detected by this signal is the triumph of nearly 100 years of experimental and theoretical chemistry, but its discovery of the conditions within this distant galaxy holds greater significance. Nebulae. And after the birth of the universe, for tens of thousands of years, the nebulae throughout the universe were very similar. Big Bang nucleus synthesis is very effective in creating atomic nuclei. but in the subsequent hundreds of thousands of years, the energy of the universe remained too high. Hydrogen and helium could not combine with electrons, forming uncharged atoms. However, when the environmental temperature drops to around 4,000 Kelvin, these unruly atomic nuclei can combine with each other in a specific order. This order is controlled by what is known as ionization. For this reason, helium is now considered to be among all the rare gases most diverse. It is the most diverse, most unlikely to react, because an electron is stripped off, and converting it into ions requires enormous energy. But in the early universe, when all existing are charged ion particles, this supreme grasping ability means he is the first element to attract electrons and capture electrons to form the first electrically neutral atom. However, this stability of helium is regrettable. Short lifespan. Due to the high temperature, isolated protons cannot capture electrons to form a hydrogen atom. Therefore, the proton turns to helium in its balanced electron supplement, seeking a way to share electrons. Therefore, ultimately, under the immense burden of these sticky particles, helium yielded, forming the first chemical bond in the universe, in the first molecule. In this process, very unstable helium-hydrogen ions were produced. Despite this instability, these short-lived molecules, for the creation of other molecules and the beginning of space chemistry, paved the way. Approximately 100,000 years have passed since the Big Bang. Astronomy has developed very well in the field of astrophysics today. Because he studied, we can expect molecules to find in space, as well as how they form. Many atomic structures found on Earth, also very common in the universe, including water and ammonia, but others are even more peculiar. For example, dihydrogen, chlorine monohydrate cation, or hydrogen peroxide. Although many have not yet been discovered, but whatever they ultimately are, their existence, ultimately it is all thanks to the helium, formed and decomposed in the first process. Hydrogen ion. You have specialized organs to perceive light and sound, the tactile sensation of solids, and the chemical subtleties of molecules. Our brain seems particularly well suited to perceive all possible stimuli that the universe can offer, but that's not the case. Reality is far more than what the eyes, or ears, or fingertips can see. Most of us can perceive with dazzling. A clear, focused, colorful image sees the world, but visible light is only a small part of the broader electromagnetic spectrum. Electromagnetic waves are in every moment of our lives. They constantly and unconsciously erode us. The food we eat, the bricks of our houses, even our bodies, can emit gamma rays and X-rays. We believe the radiation from the sun that we can perceive can contain about 10% of ultraviolet rays. It can penetrate and damage our skin and eyes. Below the energy of visible light, sunlight is composed of about 50% infrared radiation, some of which we will experience as heat. But even at lower energy levels, infrared technology, such as motion sensors and TV remote controls, can send and receive signals completely undetected. Bluetooth, Wi-Fi, cellular, mobile, and GPS both exchange information in the air through radiation of microwave frequencies. While our analog radios and televisions, the longest wavelength electromagnetic radiation is used. Radio waves. If we could see all radio waves, we would be deceived. In summary, for all our obvious perceptions, we at least do not know 99% of things in the universe. Perhaps this is also good. It's hard to imagine how our brains will adapt, can cope with all possible stimuli. A relatively calm night sky, to be a riot of colors and a cacophony of sounds, sharp points of light and singing from numerous sources. Behind all of this, everywhere are faint backlights, the afterglow of the first light in the universe. In the earliest few hundred years of the universe's existence, although it was filled with light, it was completely opaque. It is difficult for us to imagine such a concept today, but since 1/100 billion seconds after the Big Bang, photons carrying most of the energy of the universe's matter, trapped in the labyrinths they themselves created. Matter and energy occupy both sides of the same coin. After the newborn universe cooled down, pure energy transformed into matter. Subatomic particles fill the universe. The density of these particles and their intense vibrational energy makes photons fundamentally unable to penetrate the particle cluster until atoms finally form. Only then will the modern universe change. Uncharged atoms, rather than charged ions, and are the components of everything around us, because they are small in size, need a lot of such atoms to build anything. There are about 7 trillion atoms in every person's body. That's 7 followed by 27 zeros. Expand it to include humanity, and the number of all other organisms on Earth, plus the Earth itself. Then multiply by all the planets and stars in the universe. The number of atoms in the entire universe is immeasurable, but the real key to creating atoms lies in capturing electrons. Electrons were first discovered in the late 19th century. These negatively charged leptons, is 2,000 times lighter than a proton, can be considered as a singularity without shape or internal structure. At such a tiny scale, quantum physics controls their behavior. Quantum uncertainty determines why we cannot know their speed and position. We can never precisely locate a single electron. Instead, we can recognize them as simultaneously occupying what physical laws allow. Every possible position, once positively charged atomic nuclei, are produced in the Big Bang nucleosynthesis process. Electromagnetic force helps to capture negatively charged electrons, thus producing neutral atoms, hydrogen atom and capturing 1 electron, helium atom and capturing 2 electrons. But this sounds simple. The process is not easy. Electromagnetic force, 100 times weaker than the strong force that binds hydrogen and atomic nuclei together. Therefore, if electromagnetism wants to capture superelectrons and bring them into orbit, then the environmental conditions of the universe must be much lower. It will ultimately take 380,000 years. The universe expands, causing the temperature to drop to about 3,000 Kelvin. Electrons finally join the group, forming the first stable atoms. When they do so, the entire universe changed. Electromagnetic attraction pulls electrons into stable orbits around atoms. They once roamed the universe freely. Now, electrons are closely bound to their positively charged counterparts. Since the birth of matter, the first time it opened the vast space, photons trapped in a maze for hundreds of thousands of years, suddenly discovered their paths were clear. They can escape, traveling in a straight line, without immediately colliding with another particle. They are the first beam of light to truly penetrate the universe. For a moment opaque, now becomes transparent. For a moment plasma, now turns into gas, soon to be broken. Now, for the first time in the entire history of the universe to become complete, we finally have the chance to see what happened. Scientific discoveries are rarely accidental, to say nothing of discoveries that win the Nobel Prize. On the contrary, scientific progress is usually very difficult. It requires years of commitment, gradual research and investment. But in 1978, the Nobel Committee openly broke with tradition by awarding the Physics Prize that year, awarded to 2 accidentally discovered men. Early 20th century, in the small town of Homedale, New Jersey, the most accidental discovery was born because of Bell Labs. There, a 20-foot-long conical antenna was built. Just a few years after the big cone was built, a new satellite system replaced the original one, making the instrument obsolete. But Bell Labs did not let their huge hearing aids go to waste. Instead, to the researcher Arno Penzias and Robert Wilson Open, they plan to listen and analyze radio signals from interstellar space. However, when they began to observe, these 2 astronomers find it difficult to in low spirits. But a signal is discerned amidst the persistent radio hiss. They checked. He was not from nearby New York City or the local military facility. They confirmed he is not from any specific part of the Milky Way or from outside the Milky Way, but it seems to be from the entire sky. So, this noise sounds so consistent and directionless. The researchers concluded it must be due to some error inside the instrument. In fact, the cause. When they checked the antenna, they found many pigeons there. Perhaps their droppings were radiating heat, thus generating noise. In several attempts to humanely relocate these birds, after failing to rehome them, researchers took more drastic measures, ultimately clearing the doves and droppings from the bell tower. But the hissing is still there. Penzias and Wilson already eliminated from their instruments all possible sources of error. Therefore, as a last resort, they began to accept this radio noise. Actually, it might come from the entire sky. The idea, they sought advice from the astronomer at Princeton University, Robert Dicke. Dicke solved this mystery to the greatest extent possible. He has been developing a theory of early universe atom formation. Believe the Big Bang is cyclical. All atoms of the previous universe reassembled in a hot, compressed fiery sphere. This so-called reorganization will make the universe transparent and allow light to be released in the cosmic timeline for the first time. His theory predicts this light, initially in the visible part of the spectrum, like yellow-orange-gray light, still can be detected in very distant parts of the universe. The subsequent expansion of the universe will extend the early space-time until the gray light becomes redshift, beyond the perception range of our eyes, entering the microwave wavelength. Dicke originally planned to look for him himself, but Penzias and Wilson unwittingly got a step ahead. So 10 years later, it was these 2 Bell Labs researchers for the discovery of the so-called cosmic microwave background in winning the Nobel Prize, rather than Robert Dicke, regardless of who discovered or clarified the cosmic microwave background, and received praise, although the periodic cosmic model of the enemy aircraft was later excluded. But its detection represents a significant turning point in our understanding of the Big Bang, the discovery of this red fiery sphere. The gray light now extends to 2.7 degrees above absolute zero Kelvin is solid evidence, indicating that the universe indeed began in a hot, dense state, even if it can be traced back to about 380,000 years after the birth of the universe. It proves what we said about this period, the theory of how things unfold. Our earliest observational evidence suggests the early universe was a hot, the high-energy and dense universe, even containing clues about how the universe will unfold. Because while Penzias and Wilson discovered the microwave hums very consistently across the entire night sky, but later designed instruments for studying CNB, discovered very subtle changes, in some places warm, slightly higher or lower by a few 1/100,000 degrees, will make CNB a cosmic background detector. Wilkinson microwave, various extraterrestrial and priority projects such as the Planck telescope. They produced extremely detailed images of changes in energy and density in the universe over 388,000 years of history. It is these density changes, seed for today's large-scale structure, because they contain more matter, then attract more matter, become more obsessed and pull in more matter. In 100 million years, these excessive densities have become large enough to trigger the formation of the first stars and galaxies. These changes seem largely random, as expected, the result of subatomic quantum mastery in the first second after the Big Bang, by expanding to a large scale through inflation. But further analysis also revealed another strange pattern hidden in CNB. This pattern also reflected in the large-scale structure of the universe today. Before the formation of atoms, when the universe was still filled with opaque plasma, its density was sufficient for sound waves to pass through it, just as sound propagates through the air today. The origin of these waves is in the swirling energy soup of mutually conflicting attractions and repulsions, because of gravity pulling the substance toward the center of denser patches. But now, photons in the collapsing maze, squeezed too tightly, are resisting and exerting outward pressure. Therefore, these photons push backward, take away some matter, spread in three-dimensional space, forming a complex concentric ripple pattern. Just like there are so many raindrops in the pond, these compressed waves are sound waves. Therefore, they are called biomimetic acoustic oscillations by cosmologists. However, this phenomenon cannot survive after atomic combination. Once the universe reaches critical temperature, 3000 Kelvin, electrons will be captured. An atom will form expanding ripples, suddenly stop their trajectories, because the photons carrying matter spread outward now can escape unimpeded. Bionic acoustic vibrations are frozen in place. They can no longer advance further. The matter around their spherical periphery is trapped, just like when photons left him. Now, about 13.2 billion years later, the universe has expanded, but the patterns left by these frozen ripples still can be seen in the galaxy. Star cluster can be distinguished in the overall structure of the hyperstar group. Cosmologists have found biological acoustic oscillations in the modern universe. Now there are about 150 million parsecs, or nearly 500 million light-years wide, and at larger distances and times in the observable universe. Measure their size. The universe provides astronomers with what is known as the standard ruler. They can use it to measure the expansion of space. Using this information, we can simulate how things develop and predict the future development method. The mark of the first light in the universe may have extended the case of pathology, becoming his own shadow before, but he will need billions of years to completely disappear from our view. This gives future cosmologists enough time to decipher his mysteries. A bright flash ignited in the dark space. First one, then another, then a series of needles. A star cluster was ignited. It grew and grew larger, and gradually brightened under the light of more young stars. Over billions of years, it is already large enough to start rotating. If its own angular momentum, enough to stretch it to the equator, star clusters will flatten into a disk rotating at a speed of over 200 kilometers per second, completing a full rotation in about 250 million years. This young spiral galaxy in outer space captures and absorbs smaller clusters arranged along its path, collides head-on with other rotating galaxies, leading to a merger, provide new matter to the original spiral, triggering a frenzied burst of star formation. About 10 billion years ago, our Milky Way in the galactic wave spiral arm, in its prime of life, lasted for billions of years. Massive stars ignite, burning fiercely, then die suddenly. The fusion fuel it has used, emit back into the galactic clouds for recycling. This gas is rich in heavier elements formed during stellar nucleosynthesis for a new generation of stars, laid the foundation for the first planetary system at a distance of about 25,000 light-years. On the fragmented spiral arm of the Milky Way, a star like this, suddenly born about 4.6 billion years ago, just like the Milky Way itself, on a smaller scale, mirroring dust and gas. Spinning around it in a flat disk, dust turns into pebbles, pebbles turn into boulders. Finally, the boulders turn into the entire rocky world. These rock worlds revolve around the yellow star, striving for a stable position. After several catastrophic collisions, they finally enter the orbit they will occupy in the next 4.5 billion years, the third farthest from the Sun. Such a rocky world formed violently with the Sun. The heat generated dissipates, water condenses into the ocean. The atmosphere and plate tectonics begin somewhere in the ocean on the planet's surface. Slow cycle. Ignite the spark of life in some way. Stand firm. Adapt and evolve. Create in a completely new way. Fill this unique world. Chemistry becomes biology. A vast number of life forms flood the oceans, lands, and skies. Then, as if from nowhere, a conscious mind seems to be thinking about its place in the universe. Although knowing the series of events that led to the life of the Sun, Earth, and the galaxy informed us, but in our understanding of the cosmology we have created, still exists a gap. Several hundred years after the Big Bang, how are atomic clusters produced? Causing all of this, billions of years later, all of this is inevitable. Still, the universe could take different paths, utilizing the atoms as we know them, and the matter and energy that existed when the cosmic microwave background was formed, simulate the subsequent evolution of the universe. The universe we ultimately obtain is subtly but significantly different from the universe we currently inhabit, with fewer galaxies. Star formation is less active, planetary formation is delayed. In these simulations, life may be lagging or even completely absent. This image clearly seems to be missing something, the last piece of the puzzle. All the pieces can be put together. Unfortunately, the missing piece. It is a phenomenon that cosmologists cannot see at all. 384,000 years after the Big Bang, light finally escaped the cage of matter. Photons can freely travel through the expanding universe, but it loses energy as it grows. The universe may no longer be opaque, but it is dark. The intense energy formed has subsided. It will take millions of years before a new process can begin. When they merge, energy will concentrate again. This is the dark age of the universe. It's possible that almost nothing is visible, but this doesn't mean nothing happened. In fact, it was precisely in the first million years of cosmic history, in the period that followed, that scientists believed dark matter begins to shape the future of the universe. 1933 Swiss astronomer Fritz Zwicky first considered the existence of dark matter. At that time he was studying volatile galaxy cluster about 320 million light-years from Earth. These galaxies seem to be moving too fast for the galaxy cluster to maintain the integrity of the cluster. According to what can be seen and counted, a star that shines brightly in the galaxy cluster, the mass of each galaxy was estimated. The resulting number must take into account the galaxy's velocity, and to hold the galaxy cluster together, the required number is about 10 times smaller. To explain these two methods of determining quality, the obvious difference between them, Zwicky proposed, in stellar gas and visible matter, there must be hidden a large amount of invisible quality. He called it dark matter. From Duncan Matrey, 1970s. Astronomical pioneer Vera Rubin was studying the Andromeda galaxy when the rotation of the nearest spiral galaxy discovered that the motion of stars in the galaxy was a bit off. At that time, he and his colleagues studied the mysterious punched cards on the instrument readings. But for this experienced astronomer, the problem is obvious. The galaxy is expected to rotate rapidly towards the center, while the stars at the edge will move more steadily. But the punch card tells a different story. Stars at the outer edge of the seem to move at the same speed as the stars. At the central bulge, the tips of their spiral arms, spinning at an incredible speed. The only explanation for this motion is that the star itself is only a part of the total mass of the galaxy, and yet it does not violate the basic laws of motion in the universe. Calculate. Visible matter must only represent 15% of actual matter, and the galaxy must be enclosed within a larger, in the invisible dark matter cloud. Subsequent observations showed most galaxies are surrounded by such, including our own galaxy. In fact, current estimates suggest that the dark matter cloud of the Milky Way may be 15 times larger than its visible range of stars. Therefore, astronomers now believe dark matter in shaping the modern universe. of great significance, although we are still unable to detect it on a larger scale. Research indicates dark matter is 6 times heavier than normal matter, and it may have always been this way. But what exactly is it? Even after decades of collaborative research, still a mystery. One possibility is, dark matter in the universe is composed of ordinary matter, such as quarks and leptons, but it is difficult to detect them with current technology. These objects are called massive dense transport objects. They are usually referred to as metros. Such objects may be black holes of various sizes, small in size but extremely dense, a neutron star with enormous mass, formed by the collapse of a giant star in its late life, or an astonishingly numerous brown dwarf. Their quality is almost as many as stars, but not enough to ignite a major change. However, with the improvement of telescopes and instruments, we are able to detect more details. The depth of interstellar space. Due to the continuous lack of observational evidence, the possibility of these objects escaping our attention is becoming smaller every year. Currently, cosmologists are more inclined to another possibility, that most dark matter interacts weakly with massive particles, exist in the form. The corresponding nickname is weak wings. These particles will be a completely new type of particle, beyond the standard model that we understand today, but we have so far failed to detect them. They do not interact with normal matter through any known fundamental forces other than gravity, but still has very high quality or quantity of existence, sufficient to make up 85% of the missing mass in the universe. In fact, we are in particles, accelerators, and in the universe, seeking traces of these heavyweight weaklings. But with so few clues, we may still have a long way to go. Whether dark matter is strong or weak, still something completely different. He likely existed under our shadow all along, since a fraction of a second after the birth of the universe. Matter began to exist, and about 1 million years after the Big Bang, entered the dark age of the universe, began shaping the overall structure of the universe. The cosmic microwave background indicates, at the moment of atomic combination, matter and energy are unevenly distributed. Therefore, we can expect dark matter to follow as well. But in these dark millennia, all mass produced its own gravity, pulling dark matter together, making it move faster than we expected. Thicker clumped together, the imitative matter will collapse on its own. Then normal matter will follow the dark matter template, sucked into invisible gravity wells, thus creating fine threads spanning the universe. Nodes and gas clusters, they will become the nurseries for the first stars and galaxies. From this moment on, the evolution of the universe we see today has become inevitable. So far, everything that has happened, all have crossed the first 1 million years of the cosmic timeline. For the astrophysical creation of the next few billion years, laid the foundation. The universe has cooled down to give understandable physics the dominant position, for forces have stabilized and become distinctly different, determined all basic interactions. The properties and quantities of matter have stabilized to provide the composition for generations of stars and galaxies, the origin of chemistry and the ultimate creation of life. But this is not the entirety of the worlds in the universe. Over 8 billion years, as we expected, with these basic components, but 500 to 600 million years ago, right in our solar system, just before forming within the Milky Way, some changes occurred. A discovery 25 years ago clearly shows we still do not truly understand the balance of the universe. This unsettling change in the evolution of the universe, first recognized in 1998. At that time, astronomers were studying supernovae at different points in space and time. A supernova of a certain size is sometimes called a standard candle because they have known and predictable brightness and luminosity. Therefore, explosions, they have become valuable tools for measuring the expansion of the universe, because their light will stretch as the space between them expands, stretch to a redder wavelength. Our instrument, but astronomers have noticed, in the past about 5 billion years, the redshift of the supernova is greater than it should be, so they are moving away from us faster than they should. This pattern can also be seen in measurements of biomimetic acoustics, oscillations in galaxy clusters. Not only that, the very expansion itself seems to be accelerating. The best explanation we have for the recent phase change in the universe is dark energy. So throughout the entire history of our solar system, we have always lived in a dark energy, the era of dominance. Like dark matter, cosmologists still don't understand very well what dark energy really is. When Einstein proposed the theory of general relativity, he introduced the concept of cosmic constant. He represented the intrinsic energy of empty space. With the expansion of space, objectively, there is more of this energy that can drive further expansion. Finally, general relativity does not need this correction constant, but this idea in explaining dark energy discovered new life. However, the problem still remains. We do not understand why such intrinsic energy should exist. If it cannot be found in the search to explain the scale of the universe, perhaps microphysics can provide some clues. Quantum theory predicts a phenomenon called vacuum energy, where virtual particles due to random quantum fluctuations in the spontaneous appearance and disappearance. Applying pressure causes expansion. This is a promising idea, but applying this vacuum energy to larger scales, the calculation results are too high, unable to correctly explain the expansion we observe. Some cosmologists considering something completely different, a new energy field called the essence. Its way of working is opposite to normal matter. Normal energy can have an attractive force, can also be repulsive, and can change its behavior over time, but without experiments or observations that can easily detect such a force, or even confirm its existence, we are trapped in darkness. As time passes, the space around us expands. So whatever it is, our universe is about 68% dark energy, 27% dark matter, and less than 5% normal matter. It is from these components that our universe has existed for 13.8 billion years. Growth and development, following the rules that were obvious at the very beginning, and at 1/10 trillion seconds after the Big Bang, you have been observing the entire history of the universe.